I mean, sorry, Zoom online, because I'm going to be using the same sort of technology here. Let's see here. Let's see if anyone joins us or not. Finally feel like I'm caught up a little bit. Is there no one going to be on Zoom today? All right. I'm not going to be upset about that.
I can't say because I was promised the margarita.
The machine broke. We used it so much. We used it so much on Wednesday, right? So who was the drunk one? Someone here like knocked it over. Okay. All right. So here's what we're doing. Instead of having that camera set up back there, I've got this set up. So I'm recording just like at Zoom at home. I've got my camera on me and we're recording this screen also. Okay. So when I upload the video, the only difference is I'm not sitting at home. I'm standing right here. I think it's better because I can bring up different things real easily, and then I can still walk around here and we can have a interaction. Y'all ready? I actually already did the homework for this, so I'm starting to finally feel like I'm back on track. So this is what we're going to do now. We're going to go through this. Let's see. Only problem is I'm going to have to wear glasses. Okay, so we're going to be talking about 3.3. I did extend the homework. This homework, I think, was due today, and I pushed it earlier this morning. I pushed it out. We're going to do 3.3, properties of functions. In terms of our schedule, we are kind of on track here. We are, does that seem blurry to you? No? Okay. So we are kind of on track. Today's the 13th. We're supposed to be starting library of functions. We're actually going to be doing property functions. So we're one class behind at this point, right? It's okay. We'll be right. We still don't have an exam until this 22nd of September. Still got a little ways to go. It's that like. So next week, next Wednesday. All right, that's when our first test is. Any questions before I begin? See how this goes. I might need my glasses. Okay, so properties of functions. So we talked about this last time, the idea of being even and odd. Okay, so we mentioned it a little bit. We talked about even and reflections. Remember that? We're going to talk a little bit more about it today. We're going to formally introduce the idea. But there is an actual algebraic definition of what it means to be an even function. And that's what's shown here. For a function to be even, for us to say that it's even, means that when we plug negative x into the function, we get the exact same answer as we plug in positive x. So let's take a look at that and see if we can't kind of wrap our heads around that. If we're given a function, and let's say we plug in some value x and it spits out an answer, then to be even means we have to get the same thing, right? The same exact answer when we plug in negative x. When I say answer, the same height of the point. And that happens for all x's, right? So the property here, let me write it down, f of negative x is equal to f of x. That's what it means to be even. So if I pick another point, let's say I picked another one over here, x, and it spit out that point, then it's going to be the same thing when you plug in negative x over here, like that. And so we do that for all the different values. You'll start to see symmetry. And I'm just going to make up the rest. Maybe it looks like this. Maybe it goes like that. And then we'd have to basically do the same thing on the other side like that. So even functions are reflections over the y-axis, always. Okay, all even functions have a reflection over the y. Any questions on that? Okay, and then to be an odd function, we have a different equation. F of negative x equals negative f of x. So that means when you plug the two values in, x and negative x, they're not exactly the same. They're actually opposites of one another. So let me show you that in a picture. So using the fact that odd means when you plug in negative x, you get the same thing as when you plug in x. Sorry, negative in front of that. So you'll have, see, if we plug in, see, I don't like the way they write this, but I'm going to do this. Let's plug in negative x. So let's plug in a negative x value over here. Let's say it spits this point out right there. Then when we plug in positive x, right, which will be on this side, and it's the same distance. Negative x, same distance as we have positive x, right? We should not get the same thing, right? It's not, they're not going to be equal. It's going to be equal to the opposite, that negative sign there in front. So instead of going up by that much, I'm going to go down. So it'll be like that. Now let's do that for a couple of points. I'm just going to make up some points here. If I do this, then that should be here. If I do, let me see, this one right here, right? Then over on this side, it's going to be down a little bit. And if I just kind of connect these together with a curve, just make something up here. Like that. Boy, that almost looks, is that a reflection over the y-axis? Not quite, right? Not quite. If I take this and reflect it here, it doesn't land on that. If I take that and reflect it here, it doesn't land on that. So let me do a reflection. I'm going to do it anyway. Let's reflect it over the y-axis. If we do that, here's what it'll look like. This piece reflects over and becomes like this. Ooh, not very good. This piece reflects over and becomes like this. All right? They don't land on each other, right? But now reflect it over the x. And if you reflect it over the x, that red piece comes up and lands right on top of that black piece there. And this red piece reflects down and goes like this. Y'all see that? So when you have that double reflection over y then x, that's called reflection over the origin. And I did mention that last time, but that's what odd functions have. They have reflection over the origin. Okay, I think I'm going to keep that down now. All right. So this is a reflection over the origin. Origin reflection. Yes, all odd functions are reflections over the origin. Or if you want, you could say double reflections. It's a reflection over y, then x. All even functions are just reflections over the y-axis only. All right, so the book has a couple of examples in it right here for us to look at to see if these are even or odd. So why don't we go around the room again? We'll start over here. So what do you think of A here? Even, odd. Remember, it can be neither. It can be even, odd, or neither. Functions don't have to be one of those two. So what do you think for A? Even, odd, or neither? Even? And by the way, when I call on you, can you say your name? That way I can just try and remember. What was your name again? Juan? Okay, so Juan, you said it's even because it's a reflection over the y-axis. Very good. So this right here, reflected over, this is an even function. Okay, you're up. So look at the y. If we reflect it, this piece right here, if we reflected it, it would look like this, wouldn't it? And it doesn't land on the other one, right? So right away you can say it's not even, right? Do a double reflection. So reflect that over the y, it would become this, right? Now reflect it over the x. Do you see where it would be? It would look like this, wouldn't it? If we reflected that. So that doesn't land on this piece either, right? So you said neither, right? That's correct. Neither. Is that the way you spell neither? So I was taught in school, I before taught that too. What's wrong with that? See, that's why I'm math. Because that's why I like math. They give you a rule, and it wasn't always true. I didn't like that. So it's like I before E except after C, or if it sounds like this or sounds like that, or it's forget it. So, all right. All right, good. What was your name? Cecilia. Okay. Greg. All right, you got part C. Origin. So how are you thinking of it? Are you trying a double reflection? Are you just like seeing it or what? Yeah. Okay. So does everyone see that if we reflect? I'm just going to take one piece, this piece right here, reflect it over the y first. If I do that, it's going to look like this, right? Like that. And now take that and bring it over like this, and it'll land right on top of that other piece. Do y'all see it? This is hard to teach. It's like you either see it or you don't see it. So lands right on top when we reflect that. One way, another way you could do it if you're having trouble with this is when I say reflect over the y, just pick a point. I'm going to highlight this point. See that point there in yellow? Take that point and just reflect it over the y-axis. So just like measure this distance and put it right there. So you put that point right here. And then measure the distance vertically and put it down here. And you land on that graph. And you can do that for like each point. All right, can I move on? Are y'all comfortable with this? This one is odd. Questions? Odd, even, neither, odd. We're happy? Okay, moving on. All right, so now we have something different. Now we are given a couple of functions here, and we're asked to determine whether each of the following functions is even, odd, or neither, then determine whether the graph is symmetric with respect to the y-axis, with respect to the origin, or neither, all right? So here they're not giving us the picture, right? They're not giving us the picture, which means we have to verify it algebraically. So let me show you how we're going to do that. I'm going to take these examples to another page here. All right, let's start with this first one here. If f of x is x squared minus 5, all right, what I'm going to do is figure out, first of all, what f of negative x is. All right, so I'm going to look at that. I'm going to compare that to f of negative x. So that means instead of plugging x into this, I'm going to plug negative x in here. So that would be negative x in parentheses squared minus 5. Now, right. If you square this, will it be positive or negative? Positive, right? So we don't really even need to write that way anymore, right, Desiree? We can rewrite that since we know it's going to be positive. We can just write x squared minus 5, right? Now, Desiree, are these two the same? Yes. Which means that f of x is equal to f of negative x. They're equal, right? And what type of functions have that property? Even, odd, or neither? Even. Even functions have this property. That when you plug in a negative, it's just plugging in a positive. So right there, we're done. And we can say even. Now look, you don't have to check for odd, okay? You have three states that a function can be in: even, odd, or neither. You can't be both even and odd at the same time, all right? It has to be even or odd or neither. So as soon as we know it's even, we're done, we move on. All right, let's do part B. What do y'all think it's gonna be? So I'm using G first. Sorry, go ahead, what? Why do you think it's odd?
Based off of the book that we've seen so far, x squared was odd number would not be.
Yeah, so maybe the even and the odd has something to do with power. Maybe it does. In the previous problem, it was x squared, right, which was even, and the function turned out to be even. Maybe having an odd is going to be odd. I don't know. Good. So let's see if we plug that in. What was your name? Josiah. So Josiah, go ahead and plug negative x in here. You take negative x, cube it, subtract 1. Josiah, what happens when we cube a negative number? It stays negative, right? So we don't need the parenthesis anymore. I can just put negative x cubed minus 1. So Josiah, are those the same? No, they are not. You all see that? These are not the same. So since these are not the same, we can say it's not even. So now we check for odd. So to check for odd, all I'm going to do, so this means not even, because those weren't the same. What I'm going to do is, I'm going to do this a little bit different than the way the textbook does it. I'm going to take that answer that we just got and make it negative. Because remember, to be odd means that two answers should be off by a sign. Remember, it's like if it came out with odd, if it came out positive on the right side, we would go over and then go down. They're always off by a sign. So if I just take the answer we just got and multiply everything through by -1, we will get positive x cubed, what, +1? Right? Distribute the negative through to that answer. Now, are these two? No, right? They both have x cubed, but one of them is -1, the other one's +1. Therefore, they're not equal, which means this is not odd. Okay, this is not odd. Now, that was Josiah. That was a good guess. Okay, the reason why. Do you want to see the reason why? Because it does have something to do with the powers. I'll show you the reason why. I keep on wanting to write on the board. The reason why is because next to this 1 is really an x. You don't see it here, but there's really an x to the 0 here, next to the 1, because anything to the 0 is 1. And so what we have here is actually a mixture of odd and even powers together. And when you mix even and odds together, you get neither. If you have all odds, you're going to have odd. If you have all evens, you're going to have even. So why was the first problem, why did that work? Well, next to this 5, right, is a what? X to the 0. And see, 2 and 0 are both even numbers. I'm going to try and do something here. Okay. So 2 and 0 are both even. So that's why. We're getting ahead of ourselves. I just want to show you that the intuition of saying x cubed, oh, that's probably odd, because that 1 didn't work. Okay, so what's our answer here? Neither. Okay, so that's the answer for this. Neither. I before E, except after C, unless you are using the word neither. All right, next one. H. I remember complaining to my dad about that I before E thing. I can remember complaining about it. And we had this discussion. I don't know how we got on this topic, but he told me, do you know, when you look at a stop sign, when you're driving down the road and you look at a stop sign, he said the ones that have the white edge on them, those are optional. He was kidding, but he was making a point, like, why have a stop sign where some of them mean stop and some of them don't? It's just, yeah. Okay, so look, I'm going to go back to Josiah. Okay, because I think we might have learned something here. So Josiah, what do you see here? Power. Right? What's the power here? Oh, it's actually there this time, right? In the previous one, it was 1. It was a constant. So this should be odd, okay? Because both powers are odd, 3 and 1. Now we need to check, okay? We need to check. So first thing I'm going to do, I'm going to figure out what h of negative x is. So if I plug negative x in there, be real careful there because you have a double negative here. You're subtracting a negative x. So we already said that when you cube a negative, you get negative, right? So when I cube that negative, it's going to turn into a negative 5x cubed. Y'all understand that when I cube this, I get negative x, but then I multiply times 5 and just push the negative to the front. And then here, minus minus, plus, right? Plus x. Okay, these two are definitely not the same, right? Those two are not the same. All right, so it's not even. We always check for even first. And now we go check odd. So to check odd, I do negative of the answer we just got. So if I take a negative and I distribute it through the answer we just got, we will get negative and negative become positive. So 5x cubed. And then you distribute this minus through here and you get minus x. And hey, check that out. They're the same, aren't they? The original function is equal to the negative or the opposite of what you get when you plug negative x in. That's what it means to be odd. Questions? Ooh, absolute value of x. That'll be interesting. The absolute value of x. Y'all know what those bars mean, right? The bars mean that no matter what you plug in, it's going to give you that answer, but positive. Unless you plug in 0. The 0, the absolute value of 0 is just 0. So let's check this out. First thing, let's take negative number in here and plug it in. So if I take a negative number in there, what's that going to spit out? So that's just going to spit out x. Y'all agree with that? Just x. Okay. Now, is that equal to this? Is that equal to the absolute value of x? Is it? So look, if the top one were just x, right? If this was just x, then these two would be equal, right? These two would be equal. But this is x and that is the absolute value of x, right? That's something different. Because what if x was negative, right? What if x was negative? Then these two wouldn't be the same. This is the first problem that we've done where, you know what, this plugging in isn't necessarily going to get us there. So I want to take a different approach for this one. I would like for us to try and graph it and convince ourselves what the absolute value of x looks like when we graph it. Do y'all know what it looks like yet? Some of you do, some of you may not. Okay, so let's try it. The way I'm going to do it is I'm going to do a good old-fashioned t-table. I'm going to plug in x over here, and over here it'll be the absolute value of x. And then I'm going to create some points and then plot them. So 0, well, the absolute value is 0, 0. So that gives us the point 0, 0, right? We can plug in 1. Of course, the absolute value of 1 is 1. And so that would give us the point 1, 1. We could plug in 2. The absolute value of 2 is 2. This is getting boring. 2, 2, right? And then we should have 3, 3, 4, 4, 5, 5, 6, 6, right? But what about some negatives? If we plug in -1, the absolute value of -1 is +1. That gives us the point -1, 1. Next one, -2 spits out +2, so we get -2, 2. We plug in -3. Absolute value of -3 is 3, so we get -3, 3. Without graphing, I want to see if you notice something. If I plug in a number like 1, I get 1, right? But if I plug in the negative of that number, I still get 1. Remember when we were saying when you plug in x and -x and you get this answer out? That's an even function. When I plug in 2 and -2, I get the same output, right? When I plug in 3 and -3, I'm going to get the same output. So I'm going to draw the graph anyway. The graph will be in red here, 0, 0's here. 1, 1, I go to the right one, up 1. 2, 2 here. 3, 3 here. All of those answers lie on a straight line, like that. That's what the right side of the function looks like. The left side of the function, you go -1 and back up 1. -2, up 2. -3, up 3. And looks like that. So the absolute value function looks like a V, not a U, a V. It has a sharp corner right here. That becomes important in Cal 1, okay, that this is a sharp corner and not a curve, right? That's what the absolute value function looks like. And I hope that you can tell from that that it is even, because it is a reflection of itself over the y-axis. So even. Any questions? I'm actually pretty impressed that all of y'all are here. I'm happy about that. Because I was sitting there, I went, I got my laptop, I had to take the other one in, and I got a new laptop, different type, and I went and bought myself this little tablet here so I could come in here and write. And I built this thing this weekend. I was all excited. I was thinking, what's the difference between this and like you sitting at home doing Zoom? Like, what's the difference? Other than we get the margaritas, right? But so I was kind of like, I don't know. We'll see. Time will tell, right? Time will tell whether or not we like this more or not. Okay, we good? We good? We good? We ready to move on to the next idea? This is a different concept. And I think I went too far. Did I? What the heck is it? Oh, yeah, here it is. Definition. Hold on a second. Okay, I panicked there for a second because I thought it wasn't recording, but it's recording. Okay. All right, so here's a definition. The idea of an increasing function, a decreasing function, and a constant function. So the definitions for the three are here. And when you look at the definitions, I remember as a student in algebra thinking, like, this is just weird. To read it is weird. A function f is increasing on an interval I for any choice of x1 and x2 in I with x1 less than x2, then f of x1 is less than f of x2. Y'all understand that, right? That makes perfect sense. Okay, so it's confusing, the definition, all right? The visual understanding is simple, but let's try and first get our heads around what it means visually, and then we can talk about the actual strict definition. So here is an example of a function that is always increasing. So if you read it like you read a book left to right, I want you to imagine that you would be moving up, right? If it was a roller coaster, right, you're going up, getting ready to go off the drop. This function is always increasing. Now, I have this little animation here that I've created that shows a point, like that's you moving along the curve, okay? And do you see that little green line segment I've made? That's just kind of to represent, like literally, if you're like on a little car on a road, you'd be close to that, right? You're going up the whole time, right? Okay. Again, in calculus, our goal is to figure out what the slope of that green line is. It's a very hard question to answer. I'm going to give you an arbitrary function. You can go to any point on that function and tell me what the slope of that line is right there. All right, that's the goal in Cal 1. Takes, well, I'm teaching it right now. We're in week, what, this is week 4? This is week 4 that we're starting. And in my Cal 1 class, we will start talking about this concept this week. Tomorrow, I'll mention it. So we've been in 3 weeks. We're just going to get into it. So very important concept. So visually makes perfect sense though, right? Decreasing is, you know, now you're coming down, right? Now you're coming down the ride. So the line is pitched downward, okay? That's what it means to be decreasing. And then constant, well, that's when you come to the end of the ride, right? And you're coming back into the station and everyone's like all happy and then people are sick and, right? That's you just riding along. Okay, so now let me see if I can try and illustrate what this definition means. Make this a little bigger. So here's what the definition is saying. Okay, hold on. It's saying that if you take some point here, x1, okay, see that x1? And you take another point, x2, but you have to have this condition that x1 is less than x2. All that means is that the point that you pick for x1 is to the left of the point x2, all right? So as long as this one's to the left of that one, then to be increasing means that when you look at the height of the function here, that would be f of x2. That would be what you get when you plug x2 into the function, right? That's how tall it would be. That should have, what should the relationship between those two outputs be? Which one has to be bigger? If you're increasing, which one's bigger? X2. So if we have this, then f of x1 must be smaller than f of x2. This is what increasing means. Does that make a little more sense now? To be increasing means if you pick me 2 points, or one of them, x1 is to the left of x2, then I promise you, if it's increasing, then the height of this point will be higher than the height of this point. That's it. Decreasing, what changes? What's the only thing that changes in this? Does this sign change though? If you pick a point to the left of this one, right? x1's to the left of x2. That doesn't need to change. What needs to change is this. Now we need the x1's value to be bigger than the x2. Let's look at the picture. Okay, hold on. Let me clear it over here. I think what I'll do it on that side. I had to get a new mouse and I have like 11 programmed buttons on here that allow me to do a bunch of things. And it's a new mouse, so I'm like trying to learn it. I just got this mouse yesterday, so bear with me. All right, so here we go. This one, so for decreasing means that if we pick some point x1, x2, if the x1 is less than the x2, then to be decreasing means that when we plug this function's value in here, f of x1, that's now going to be higher than this point, f of x2. So f of x1 must be greater than f of x2. Okay? So this stays the same, but this inequality gets flipped. Any questions there? All right, moving on. So that's this now. That's what it means. This one, these two flipped, right? These stay the same. And then look, to be constant means that no matter what you plug in for x, no matter what you plug in, all the rest of x's are always the same. All right, so here's a problem. I need to make this a little bit smaller. Determine where the function is increasing, decreasing, and constant. Now, very important. When we talk about where a function is going up or down, or where it's constant, we're always referring to the x values where it's happening. Always referring to the x values. So let's see. You're up? Lorena, okay. So Lorena, can you tell me where, well, I'm gonna just come over here and you just tell me when the function starts to be increasing. Okay, I'm just moving along here. Okay, from here, now you're on the roller coaster, right? Going up. All the way to here, right? So what we're interested in are the x values where it starts and ends, right? So Lorena, you said from here to here, we're going up like that. And so the corresponding x values are -4 to 0, -4 to 0. So our answer will be, I'm going to write it this way. Write f with a little arrow going up to represent increasing is happening from -4 to 0. Now, interesting thing here. I could have also put -4 to 0 with brackets. Both of these answers would be correct. And when I was doing the homework, I was curious to see what the computer was going to do. And it turns out that the computer took this answer. This would also be correct though, because the difference between these two answers is where you're starting. Here we're saying that my answer on top says starting at -4, not including -4. But see, there's a solid up here, so why am I not including it? Right? Why is it so correct? The reason it's correct is if you talk about increasing or decreasing or constant, no matter what, you always have to be talking about two points. And so if you take the endpoint off, it does not impact the idea of increase. It's a subtle thing, but my recommendation is that you just always use parentheses. Anytime you're talking about increasing and decreasing, just always use the parentheses, because had this been an open hole, then the bottom answer would not have worked. Only the top answer would have. So to be safe, just stick with parentheses. Okay, Lorena, was that the only place it was increasing? Okay, we move on. Josiah, right? Okay, so you do decreasing, all right? So starting from here, right here, okay, and then to here, right? And then we keep moving there to here. So we want the x values, right? So can you tell me this region here in terms of the x values where we are decreasing? -6 to -4, right in here and right in here. So the x value is -6 to -4. So I'm going to put f decreasing -6 to -4 parentheses on both. Does everyone agree with that? Any questions on it? Okay, where else? 3 to 6. Now I would put a union between those, but in the computer for the software, they want you to put a comma. All right, good. And let's see, sir. Adam, okay. Juan, Greg, Lorena. Say, Cecilia, I want to say Giselle. I don't know why I want to say that. And then Desiree. Okay, let's do it again. Juan, Greg, Cecilia, Lorena, and then Desiree. Okay, Josiah 1 and 2, Adam. Okay, I'm not going to remember these. If I can remember everyone's name by the end of the semester, I'll give everyone 5 points on the final. Yeah, plus the 8 from the Zoom, yeah. But you're not on Zoom today, so you're not. Okay, so Adam, where are we constant? 0 to 3, okay? So, but the thing is, always the x coordinates, right? Always the x. It's the interval that we're looking for. So I'm gonna put here, straight across, oops. Still getting used to this pen. And then you said 0 to 3? That's it. Okay. We good? Makes sense? Yes. Lorena, yes?
On your test, if we put like comma or like the union sign.
And no big deal. Yeah. Okay, we are moving along, All right, new definition. The idea of what's called a local maximum, local minimum. Local maximum, local minimum. So again, this is one of those definitions where when you read it, you're like, what? So I'm going to read just the one for local maximum. A function f has a local maximum at some value c if there is an open interval in I containing c so that f of c is greater than or equal to f of x for all x in this open interval. The number f of c is called the local maximum value of f. Obvious, right? It makes perfect sense. So again, the visualization of this is not difficult, okay? So let me take you to a visual. Oh, hey, I forgot to show you all this one. Look at this function here. Increase, decrease, increase, right? I just want to show you. Okay, look at this one here. Increase, decrease, decrease, increase. Everything in green is the increase regions. The red is the decrease, right? So we have, this picture is good for demonstrating what local max and local min is. You see this point right here? This point right there is called a local maximum. Yes. So that's a tricky question, because what Adam is referring to is right there. Is our function constant there? No. Now, here's why. To be constant means that you pick me 2 points and they have the same height, okay? That is the highest point on that graph. If you move a little bit to the left or a little bit to the right, it's going to be below. Do y'all see? Do y'all understand that? That's an important observation to make, though, that if I were to take a point a little bit to the left of it, I would be below it. I'm sorry, a little bit to the right or left, either side of that point. So this is perfect leading into what we're about to talk about. This point right here is called a local maximum. And the reason it's a local maximum is because at that point is higher than all the points around it. Locally, it's kind of like that point's the king of the hill. Okay, only that hill. Because you see how the function goes up over here? There are points on this graph that are higher than that point. But locally, that is the highest point. So we call it a local maximum. Make sense? It's not constant, though. We would need it to be flat for a little bit. If it went just, for a little bit flat, then we could say. But again, in Cal 1, that's something we're interested in, though. We want to know where that peak happens. Is that a question?
So the next one. Is there a constant?
This one?
Yeah.
It's not, because we'd have to zoom in, but it's not an interval. Like, we have to zoom in. There's a little bit of a gap in here.
Oh, right.
It's hard to see it, but there's a little gap in there. It looks like it flattens out. I mean, if I sat there and told you it flattened out, then you could say yes, but here it doesn't. Okay, so the idea of a local maximum is the highest point locally. A local minimum is the lowest point locally. So that would be a local minimum, that would be a local maximum. Let me do another, I'm going to draw my own. Okay, these masks. You don't feel the need to copy that down exactly, all right? This graph has a bunch of intervals, where it's increasing and decreasing, right? There's no places where it's constant, but there's a lot of increase, decrease. Now, there are also multiple local maximums. We have a local maximum here, here, and here. Those 3 points are local maximums. And so when you talk about a local maximum, you talk about it as a point. Okay, so whatever this value is, let me just make it up. Let's say that this was -5. Then this would be the point -5, and I'm going to make up this point 10. So that means that when you plug in -5, it spits out 10. So the value of that local maximum is 10, and it happens at -5. Okay, so at -5, you have a local maximum of 10. Make sense? I'm going to put another one here. How about, let's say this is 3. I'll tell you that that's 3, I don't know, 15. Then let's move around, sir. Hugo?
Yeah.
Okay, I'm going to put another point here. How about 7, 3? So is it Hugo or Hugo? Hugo. Hugo. Oh, I'm wrong in both cases. Okay. Hugo. Okay. Juan, Greg, Cecilia. Hold on. Oh my gosh. See, that's how bad I am. Don't say anything. It'll come back to me. Josiah, Adam, Hugo. See, he threw me off. Come back. Desiree and Lorena. I'm gonna do this. Don't give me a quiz next time. Okay, Hugo. Yeah. I would like you to tell me where this function, where it has local maximums. Where? Okay, -5, 3, 7. Now, what are the corresponding local maximum values for those? 10? Just the 10. So the value is the y coordinate. What you gave me first was where they occurred. -5, 3, and 7. Perfect. Now, if I say, what are the values that correspond to those? 10, 15, 3. Got it? The thing that's kind of nice about this section is it's very visual at this point. And a lot of people do good with visual. Let's see. Who wants to go? Your table. Go ahead. What's your name? Carissa. Wait a minute. What's your name? No, Chris. Cecilia. See, this is my brain can't process this. Okay, Cecilia, Carissa. All right, Carissa. I have labeled in green what we call the local, what do you think? Minimums, right? So local max up top, local minimums. All right, where do they occur? Tell me where the local minimums occur. -3, 5, and 10. Good. And what are the corresponding local minimum values? -2, -1, -12. Right? So values is the y coordinate. Where it happens is the x coordinate. All right, that all makes sense? Local max, local min? Okay, now we're going to talk about, and I'm not going to put the definition up here yet. I'm going to show it to you after. We're going to talk about something called the absolute maximum and the absolute minimum. Or another word for it is global maximum or global minimum. So what do you think we're talking about when we say, hey, what's the absolute maximum? Yes, yeah. Yeah, the y values are always going to give you the actual value of the minimum. Well, in this case, the greens. The x coordinate gives you where they occur. So I could say, oh, look, this function at 10, I have a local minimum value of 12, negative 12. At 10, I have a local minimum value of negative 12. At 5, I have a local minimum value of negative 1. At negative 3, I have a local minimum value of negative 2. So absolute maximum minimum. Carissa, we'll continue. What do you think? What do you think I mean by absolute maximum? Let's stick with that. Absolute maximum or absolute minimum, your choice. What do you think I'm talking about? The highest, right? The absolute maximum would be the highest point, right? So Carissa, looking at this graph, be careful. Do you see a highest point on the graph? Careful. What does that mean, Carissa? It's going. And that means forever because I didn't tell you about that, right? So could there be a highest point? Not one that we see. So it is implied by that arrow that it keeps going up forever to infinity. So Carissa, that means there is no absolute maximum here, okay? The highest point on the graph here doesn't exist because of that arrow. Now, Carissa, I'll move on. We'll let you off the hook.
Okay.
Amanda, you know, I'm going to work on this side of the room, okay? Because I'm ready. I think I'm going to lose it. Yeah. Okay. And it's so disappointing when, you know, I can't say your name. I just feel so terrible about it. Okay, so Amanda, absolute minimum. You see a lowest point on the graph?
Negative.
This one?
Yes.
What about that one over there?
It's closed.
It's closed. Is the Y value of that point below this one?
Yes.
Now I didn't label it yet, right? I should probably label it. How about I label it negative 9, oops. Negative 9, negative 15. Yeah, so this would constitute the absolute minimum of the function. And it would happen where?
The negative 9.
At negative 9, what is the value? Negative 15. That makes sense? Does that make a little more sense? Okay. So we can have a bunch of local stuff happening, right? Locals, not local, local. And then we can absolute max and min, it depends. Okay, it just depends on the graph. All right, how are we doing on time? So let me go back up here to this problem here. Yeah, this one looks good. Okay, so here's what we want. Here's what I want to know. I want you, why don't you work on this? Okay, you can talk to each other or not. Here's the things I want to know. I want to know for this graph, where is this function increasing? Where is this function decreasing? I want you to find any local max. I want you to find any local minimums. I want you to find any absolute maximums and any absolute minimums. So I'll give you a little hint as you start this. For the first two, your answers are going to be intervals, okay? Because that's where it's going up and down. The local max min, absolute max min, these are points, all right? So see, let's take a few minutes, see how you do with that. If you have a question, please raise your hand. I'll be happy to come by and help you. I mean, let's take advantage of the fact that We're here face to face. I'm on your way. Okay, I've got to be able to share that at home. That helps. Are you all ready? All ready? Anyone need a little more time? Yes, a little more time. All right, Lizana. Where's Lizana? That's right, okay. So I'm cheating. I have the roster up here. It's gonna help me think. Lizana. Okay, Lizana. How about F increasing? What do you got? -1 to 1, so here to here, and then from 3 on forever, right? So you said -1 to 1, union or comma if you're doing your homework, and then this was, you said 3 to infinity? That come out okay over there? Yeah, that's good enough. Y'all agree? Yeah, good, okay. Let's see here. Amanda, we've done. So, Tavia? Tavi, okay, so don't go off of this. Tavi, okay, Tavi. All right, Tavi. -infinity to -1, union 1 to 3. What do y'all think? We're good? I'm not gonna even look. If y'all disagree, let me know. Trusting your classmates. Good, that's where it's going down, looks good. Okay, where are we at? Michelle? All right, Michelle. Local maximum. Where do you see a local max? You can give it to me as a point. 0.2, what do you mean 0.2? Not sure. One, this one right here, yes. So just 1, 2. You can just say 1 at the point 1, 2. Y'all agree? Locomax, like this is the king of the hill, it's the king of that hill. That's the only hill it's the king of. So 1, 2, Locomax. Any other local hills, hilltops, Michelle? No, that's it. How about local minimum? So we're looking for valleys, lowest points. You can give it to me as a point. Yeah, -1, 1. And then do we have any others? It would be 3, 0, that one right there. So, and 3, 0. Okay, good. All right, volunteers now. Absolute max. Josiah? You just say none. None. Absolute minimum. 0. Okay, now the minimum value, okay, the lowest this graph gets is 0. As a point, you could write it as 3, 0. But the minimum value, right, the lowest value it takes on is that 0. All right, is this all clear? Any questions? Yes.
For either the local max to also be the absolute max as well?
Absolutely. Yep. So here, the local minimum, one of our local minimums was actually also the global minimum or absolute minimum. All right. So this is the definition for absolute max and min. Not going to go through it. So depends on what they ask you for. If they want to know the absolute maximum, right? The absolute maximum of the function, it'll be, if they're asking for the maximum, you're going to give the y value. Or if they ask you for the absolute minimum, it's the y value. If they say, where does it occur? Then you have to give the x value. And the language in the homework is easy to understand because it'll tell you like, where does it have a maximum, you know, and it'll tell you, give the x coordinate where it happens. And then what is the value of it? And then you put in the y coordinate. Okay, so here, we're gonna go through these quickly, all right? So I'm gonna label first the absolute, the local maximums. Local max, local max. Now, even though the graph stops here, that is locally the highest point. It's the king of that half hill, right? It's only half a hill, but it's the king. So we have 2 local maximums. They occur at 3 and 5 respectively, and the values of those are 6 and 5 respectively. Make sense? Local minimums. Here and here, right? 2 local minimums. What about absolute maximum? 6, and it happens right there. That's your absolute max. And absolute minimum would, the absolute minimum value would be 1. Absolute maximum value would be 6. They occur at 3 and 0. Next one. Ooh, this one's tricky. Local maxes. Local max, local max. The 2 endpoints are local maximums. They're the highest points in their little neighborhood. What about a local minimum? Tricky. Does not exist. Okay, there is not one. And it's because that hole. Now it's hard to understand why, so I'm going to do my best to try and explain it over here with it. I'm going to exaggerate what's happening there. This is an exaggeration of what's happening right here. You cannot tell me what the lowest value is because this gets closer and closer. The open hole means you get closer and closer to this y value of 1, but you never actually get there. Because there's a hole, you can't actually get to -1. I'm sorry, positive 1. So you do not have a local minimum. Is that clear? No local minimum. No local min. And then this would be a local max. This would be a local max. And as far as the absolute max, you would have that would be your absolute max. What about an absolute minimum? None. If you don't have a local, you can't have an absolute. So no absolute minimum. This is the good one. The one on the left, local maxes, right? Local maxes. What about local minimum? This is tricky because it's like a little straight line segment there. Do you see that straight line segment here? Go straight across. So to be a local, let me go back to the definition of what it meant to be a local minimum. Where is it? You see this? The maximum said that at that point it had to be king of the hill, right? Which meant that it had to be bigger than or equal to everything around it. Bigger than or equal to everything around it. Made it a local max. Less than or equal to everything around it to be a local minimum, which means it can be at the same value, okay? What that means in this case is that every single point on that line is a local minimum. Every one of them. Now, what is the local minimum value? 1. Where does it happen? Every point in here, right? Which you couldn't list them all out. But the local minimum value is 1. Happens at an infinite number of points in there. The local maximum value, well, we have 2 of them, right? 3 and 4. And it happens at 2 many points. Do we have an absolute maximum? Yep, 4, and it happens right there. Do we have an absolute minimum? The lowest value on this function? 1. We do have an absolute minimum. Okay, last one. Local max. No local max, right? No local max. No global max. No absolute max, right? Goes up forever. This left endpoint is a local minimum and the absolute minimum. Both. It's both. Locally, it's the lowest, and globally, it's the lowest. All right, this all good? Okay. That was one last one. We'll move on. All right. So in calculus, we have a theorem that becomes very useful to us. It's called the extreme value theorem. And we're not going to get too deep into it, but we're just trying to expose you to it in this class so that if you do, how many of you need calculus? Yeah, most of you do. Okay. So this theorem will come up again, but just want to see it for the first time here. It says here, if a function f is continuous, and then they put a little asterisk here because we haven't defined what continuous means. The general idea of a function being continuous means that you can draw without picking up your pencil. That's what a continuous function is. You just draw it, you never pick up your pencil, and it's continuous. So some examples of continuous functions, obviously that would be continuous, right? You could make it real crazy. You can make it do a bunch of crazy shit. As long as I don't pick up my pencil, and as long as it passes the vertical line test, right? I can't do this, okay? Because that's not a function. It fails the vertical line test. So it's not to be a function. But if you have a continuous function, so this wouldn't work either. I couldn't do like this and then like put a hole and then come down here and continue. That would not be continuous. I have to pick up my pencil to draw this. That's the loose definition of continuity. And in calculus, we have a more formal way of defining it. So it says, if you have a continuous function on a closed interval, then f has an absolute max and absolute min. Guaranteed, you must have an absolute max and min. Now, what makes this theorem true is this. What it's saying is it's almost a challenge. Let's say I ask you to draw a function that starts here at A and ends here at B. So we have a closed interval. And I tell you the function, it has to be defined on this closed interval. So it has to be defined at the left endpoint and defined at the right endpoint. And you must draw it without picking up your pencil. Okay? No matter how you draw it, doesn't matter. As long as you don't pick up your pencil, no matter how you draw it, you're always going to have an absolute max and an absolute min. You have to. There's no way around it. You can make it do whatever you want, but you're going to have a highest and lowest point. Right? Can anyone think of something I could draw to challenge that idea? Straight line? You mean like start and go straight across? Does that have an absolute max? This is a good challenge. Does that have an absolute maximum? Yeah, let's give it a value. Let's actually say that this, let's just say that this was like up 2 units. Okay? Straight line. So the absolute maximum of that function would be 2. And the absolute minimum would actually be 2 also. So for a straight line, the absolute max and min are the same thing. That's the kind of one exception. If you do it any other way, you're going to have it like an obvious highest and lowest. Okay, good. That's it. That's all we're going to talk about this in this class. Just a quick little introduction to the theorem. You won't be tested on that. All right. Now we want to talk about average rate of change. We got about 25 minutes. Y'all doing all right? Okay, we're going to finally kind of shift away from us just looking at a graph and like thinking, oh, where does it go up, down? We're going to talk about some other things that are going to be algebraic things that we need to do. And then we're going to tie it into, again, calculus, where we would see it later. So the average rate of change. So I like to think of this with a visual before we get too deep into it, just a visual. I'm going to do a graph here. Oh, try that again. Let's say that the x-axis is time. And let's say it's measured in hours. And let's say that the y-axis is distance. And let's say it's measured in miles. I want you to think about you driving here today. I'm assuming you drove. Someone drove. Maybe you walked, but you're sitting there, you're in your car, you're in the driveway or whatever, and you're getting ready to leave. And then you're going to start the clock, okay? You start the clock, and so at the beginning, your time is 0 and you've gone no miles, right? And then you start driving here, right? You drive, blah, 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 and you drive. And let's just say, for the sake of easy demonstration, let's say that it takes you 2 hours to get here. You drove from Austin or something, right? Margaritas, you drive a long way from Margaritas. So it took you 2 hours to get here. And let's say in that time, you went 84 miles. That dot would represent the end of the trip, right? After 2 hours, you've gone 84 miles. What was your average speed? You went 84 miles in 2 hours. What was your average speed? So we need to understand what average speed is. There's a formula for it. The average speed is the total distance that you travel divided by the total time it took you to travel that distance. So in our case, the total distance we traveled was 84 miles, and it took us 2 hours. So we got 84 divided by 2. That gives us what, 42? 42 miles in 1 hour divided by an hour. So 42 miles an hour was your average speed. Does that make sense? Now, does that mean that the whole trip you were driving 42 miles an hour? No. I mean, sometimes you're sitting there in traffic, right? The other time you're like flying by, get the hell out of my way, all right? Weaving in and out of traffic. You're that person, right? So if you were to graph your actual trip, it would look whatever it looked like for you driving, right? So it might look like this, right? That's what Greg's looked like, right? Juan's looked, if did the same trip, would look like something else, right? Everyone's trip is going to be different, agreed? But the average speed is going to be, if this point's here and this point's here, the average speed is always going to be 42, right? What happened in the middle is going to depend on the driver. With me? Now, visually though, if we were to connect these 2 points with a straight line, right, with a straight line, then there is a nice relationship between this 42 and that line. And it is the slope of the line. So if we go back to what we learned about lines, this right here is called the rise. And this right here is called the run, right? Do I remember this? And slope of a line is defined to be the rise divided by the run, which in this particular case, the rise is that distance, right? 84 divided by the run, which is this time, which is 2. And that's the 42. And it would work like this for any trip. So the slope of this line is the average speed, all right? And that becomes very important in calculus, this idea, all right? This very simple idea, because we do something with it. So what we want to look at now is a definition that's very similar to this idea, and that is the idea of an average rate of change. Let me get to that slide if I can get to it. The average rate of change. So if A and B are such that A is not B, if those are 2 points in the domain of a function, the average rate of change of the function from A to B is defined as this. Now this formula looks like terrible until you see it in action. So I'm just going to put it right there. So it's saying if we have a function, okay, so I'm going to just come in with that same picture I just drew a second ago. And I'm going to stick onto this number line some point A and some other point B, right? So for us in the previous example, it was 0 and 2, wasn't it? 0 and 2, but here it's A and B. Well, when we plug A into the function, we get some point here. This would have the coordinates A, f of A. Now, we don't know what f of A is because we don't know the function. For us, in the previous example, it was 0, 0. But here it's just A, whatever A is, and whatever we get when we plug A into the function. That looks terrible. Let me fix that. F of A. And then the other point, I don't know where it is. I'm just going to make it up. Let's say is here. That would be the point B, f of B. Now, the function can do whatever the hell we want it to do, okay? In the middle, I don't care what it's doing. Okay? I don't care about that red part. What I care about is the average rate of change. The average rate of change is exactly the slope of the line connecting the 2 points. Because just as before, I can draw a little triangle. This is your rise, and this is the run. So here's the big question. What is the rise? What is it in terms of this function? Can you all look at the numerator? Look at the yellow up there. That's the rise. But why is it f of b minus f of a? Yeah, look, it's this distance here, right? Which should be the difference of the y coordinates of these 2 points. So if I take that y coordinate and I subtract that y coordinate, that'll give me this difference. And that's why that's the top. So this right here is equal to the f of b minus f of a. And then the run is the difference of the x coordinates. So this is b minus a. And that is the bottom piece. So do y'all see that this is just really kind of a fancy way of writing the slope or the rise over run for a particular function at 2 points? We don't want to get carried away with how messy it may look. Now we use some notation here. You see that right there? Do y'all know what that little triangle in front represents? You know what that is? It's a symbol that represents, it's called the delta symbol, but what it stands for in math is change. So that means change in y divided by the change in x. So we're taking the change in the y coordinate, rise, and we're dividing it by the change in the x coordinate, run. Right? So that's just another way of writing change in y over change in x. Okay, let's do an example with this. Find the average rate of change. There's 3 parts to this. We want to do it part A, we figure it all out, then we go part B, figure it out, part C. So what I'm going to do is I'm going to do part A. So what they've given us here is A and B, all right? They've given us those 2 points. And now what we need to do is calculate what is f of B minus f of A over B minus A. Hold on a second. It's my first time using this. I wasn't sure how long the laptop would go. Plugged in. But I've got a ton of things running right now, so let's get some power on there. I haven't had to buy a laptop in a while. I'm just blown away. I don't know if any of y'all are technical geeks, but have y'all ever heard of a Thunderbolt connection on a computer? Thunderbolt? It's a connector. It's tiny. It's this tiny little thing right there. This little, they call them USB-C, but it's different. It's Thunderbolt. So anyway, same connection, but you can send through that one little tiny connection, you can send power, data, like I can project to 2 high def 1080p displays all through that little, it's crazy. I'm going on top. I was like, oh my God, I cannot believe how much you can do now. All right, where's my pen? There it is. Okay, so understand I'm just going to apply the formula and I'm going to replace B with 3 and A with 1. That's all I'm going to do. So it's going to become f of 3 minus f of 1 over 3 minus 1. Now, f of 3, I have to use this function that they gave me. Plug 3 into it, right? So what do we get when we plug 3 in there? 27. So 3 squared first is 9 times 3, 27. Minus, then you plug 1 in. Just get 3, and then over 3 minus 1. So 27, take away 3 on top is 24. Divide that by 2, we should get 12. Make sense? This is, do you all think that that's pretty simple as far as like what you're doing is mechanically plugging things in? Apply the formula? You think you could do the other two? Yeah? Now, I want you to see it visually, though, what we just did. So what we just did right now, this is the graph of that function, 3x squared, okay? That's the graph. And what we just did was we said, hey, let's go from, what was it, 1 to 3? So here was 1 and here's 3. And what we said was, let's look at the function just in there, okay? And ignore the rest of it. And let's connect these two endpoints with a straight line. And then said, what's the slope of that line? That's what we just did. And what did we say it was? 12, right? That point, sorry, just ignore that point, actually. That number is representative of the slope of that, okay? Understand? That black line has a slope of 12. So that's kind of like your average rate of change, just on that little segment. In part B of the problem, they want you to go from 1 to 5, right? From 1 to 5 instead. So visually, what do you think is going to happen if I go from 1 to 5? So 5's out here, 5 up here, like that. Do you think that that line's going to get steeper, or what do you think? Let me move the point. Watch, I'm going to move this point B. I'm going to have to move this out. Watch what happens to the slope of this black line. You see it? Now I'm going from 1 to 5, connecting with straight line. Look what the slope is now. 18. So when you do part B, you should get an answer of 18. And then for part C, it wants you to go from 1 to 7. So that should be even further out. Let me see if I go 7 here. Wow, that's way out there. There it is. Now you can see very steep, 24, right? Here's what you do, just to give you kind of a preview. Here's what you do in calculus. We're not ready for it, but you might appreciate the idea. Okay, you see the slope of the line right now is 15. I'm going to move that second point, the one on the right. Right now it's at 4. I'm going to move it over to 3. Now the slope's 12, right? Now I'm going to move it to 2. The slope's 9. I'm going to move it to, what happens if I move it to 1? Undefined. What happened? The 2 points went right on top of each other. And when 2 points are on top of each other, what's the rise over run? Well, rise is what? And what's run? Division by 0. Division by 0. And that's a problem, right? That's a huge problem. This is the problem that Newton was trying to figure out. How do we get around this? Because, let me change one thing here. Let me step this to 0.001. Do you agree that as long as these 2 points are not on top of each other, we do have a slope, right? We have a slope. You see it, 9.9? Watch as I move. I'm going to move that point closer. Watch what's happening to the slope. What is it? 9, 8, 7. what was it, about 6.18? About 6.18. Can I get it any closer? Ah, shit, I can't. You see, it's like, it looks like it's headed towards 6 though, right? Maybe if I could get a little closer, it'd get closer to 6. That's exactly what calculus is doing, is trying to figure out what would happen if you split them on top of one another. And we find a way to get around that whole idea of division by 0, which is remarkable because it's what allows us to have everything we have technology-wise. Everything is based on that, calculus. Okay, we are running out of time, 9 minutes. So the last thing that we need to do now is remember something from another math class that you took before this, and that is how you find the equation of a line. So we should all be comfortable with the idea that we can always find the equation of a line if someone gives us 2 points, right? If you have 2 points, you should be able to find the equation of the line. Also, if somebody gives us a point and a slope, then we should also be able to find the equation of a line. That is, if somebody gives us the slope of a line M, and they give us a point on that line, then we should always be able to come up with the equation using what's in that blue box there. So I'll give you an example. What's the problem that we just did, right? What was the point that we were given? I'm sorry. Well, let's just do an example. I think it'll work out better if we do an example. Let me go back to this one. Okay, this one right here. Okay, we found the average rate of change, right? From 1 to 3, we found the average rate of change to be 12. And I told you that's the slope of that line, isn't it? That's the slope of that line. So do you agree right now that in this problem, I have the slope of that line? It's 12. Do I have a point on that line? Do I have a point on that line? What's the point that I have? Well, 1 is the x coordinate, isn't it? Yeah. And then 3 is another x coordinate. Okay, yes, yeah, make sure. So Ugo is saying, if I plug 1 into that function, I get 3, don't I? So I do have a point on that line. It's the point 1, 3. Now, Ugo, I also have another point, right? I could plug 3 in here into there and I get 27, but the formula requires only 1 point. 1 point and the slope. Once you have that, you can come up with the equation of that line. So let's do it. For this particular line, what would be the equation of that line? I'm out of room, so I'm going to copy this real quick. So for this problem, the equation of the line would be, I have to use the formula y minus y1 equals m times x minus x1. And I know my x1 is 1 and my y1 is 3. So it's just plug and chug now. Just plug the values in. So y minus 3 equals 12 times x minus 1. And this is the equation of the line. Now I'm going to clean it up. I'm going to distribute the 12 through the right-hand side. And then I'm going to add 3 to both sides. So when I add 3, add 3, add 3, you get -9 instead of -12. Go with me? So I'll go back to my graph one last time, and I'm going to start a brand new graph. New blank graph. And I'm going to have it graph for me y equals 3x squared. There it is. Okay. I'm going to have it graph the point 1, 3, which is the point Ugo said was on the graph. You see it there? 1, 3. I'm going to have it graph the point 3/27, which is the other point that was on the graph. Where is it? Right there. Okay. We just found the equation of the line that should go through this point and that point. And we said it was what? 12x minus 9. Y equals 12x minus, here we go, 9. There it is. It goes right through those 2 points. And that represents our average rate of change from one point to the other. One last thing. That line has a very special name. It is called the secant line. Okay? So anytime you have a function, and you pick 2 points on that function, and you draw a line through those 2 points, it is referred to as a secant line. All right? It's just language. Secant line. And the slope of that secant line, M with SEC, that is exactly the same as the formula that we had for average rate of change. So these are all interconnected. The average rate of change is this formula, but it's also the slope of this secant line. And that's it. Okay, I think we're at the end here. There's no more material. That should take you through the homework. Should be no issues there. Yeah. Okay, so I'm going to stop the recording. Are there any questions?